Today I'm going to talk about the other JavaScript performance, or as subtitle says, no one is talking about. Unfortunately, this subtitle will no longer apply after today, so if you have any creative ideas how I can change this for the future, feel free to reach out on Twitter or Mastodon or any other social network using my handle Miroslav. And let's see what is that performance that everyone is talking about. So if you've been to any conference lately or just checked the program or a schedule for the conferences, you might have seen the inflow of different performance talks. This is just from one of the conferences that I attended, where there was talk about optimizing Framework X for performance, future of performance tooling, high-speed web, plus a couple of others, which I didn't put on this slide because there are only 3 Spider-Mans, and I didn't find a picture with 7 or 8 Spider-Mans. So I only left these 3. There are some other talks talking about performance, but a different type of performance. So not this guy, he's talking about monorepos. So if you listen to any of these talks, usually they mention some abbreviations like LCP, TTI, FCP, TBT, MBA, LSD. And all of them are saying, hey, you should use static websites. You should pre-render everything to static. Or you should use your perfect favorite 3D modeling application and render the server side. Or you should lazy load everything. You should hydrate a lot, or at least partially hydrate, or as they call it, use islands. Now, all of these promise that if you use all these tricks, your websites will be performant, and that all of this is enough. But is it though? They forget to mention that there are JavaScript applications that don't necessarily run in a browser. They never see the world of HTTP. They only run on your machines as CLIs or node applications. So for them, this type of thing doesn't apply. On top of that, application spends at maximum 10% of your time as a user while loading until you get fully interactive website. So all of that remaining time, the remaining 90% time, happens after all this preloading and all these magical things that everyone is talking about. So what if your website is slow after the initial load, after everything is done? How can you approach this? How can you speed it up? Despite what some people might say, there is a website after initial load. So all of these tricks that I'm going to show you today, they have all been battle tested on different applications. All of the snippets that I will show you will have also QR codes where you can check the benchmark tests. There will be times when you can take a picture and go to the benchmark test. You don't have to do it now. I'm going to post all the slides so you can do it later. For now, it's enough if you just trust me that these results are valid. So let's start with the big elephant in the room, the big O. Don't worry, I won't go too much into algorithms and computer science. This is the important diagram just so that we are all in the same picture, that O of 1 is pretty much static algorithm, so it doesn't change as your data changes. Then you have something like logarithmic or a linear one, which changes slowly as your data increases. And then you have this focus on the left side, which is exponential ones, that as the number of your, or size of your data grows, your application becomes tremendously slow. Now, the important thing for this is that all of these algorithms depend on the number of loops, because n is the size of your data, so you can't really influence this. If the size is big, it's big, that's it. What you can do is you can influence the number of loops. So who can tell me how many loops you can see on this snippet? Who wants to guess?
3 at least?
Okay, let's see. So first is for. Then we have for each. Then we have for in. And finally, we have spread. This is also a loop. So if you have n elements in these initial values, it will create a loop with a length of n that will have to decouple the entire array and then, or entire object, and then spread it again. So these are some of these hidden things that you might not notice, but are actually slowing down your application. So you might see just one for loop. Oh, it's simple, it's just O of n. But then you might have a couple of spreads inside, and it's no longer O of n. It becomes more complex. It's also...
Number 2 not?
Sorry?
Line number 2 not?
Yeah, number 2 as well. So all of these are loops.
I mean, that will be 5 then.
It means it counts, the line with counts also is a
I
loop.
think looping over to element.
No. So this is just plain lookup. So nodes, in this case, is some sort of array because we have length. So nodes of I is just picking up the element on the position I in the array.
Looping to the element.
It's not looping to the element. It's just taking it from the memory position. So it's not doing any looping. It's just you tell it, hey, this is your array, and this I is a position in the array, which translates to the memory position from which you just take the information. Now, important is also to know how these different loops perform. I have benchmark somewhere which I didn't prepare for today, but that shows that the fastest one is for each, followed closely by for loop, and then all these for in, for off, and all the other variants are so slower than that. So if you can always use for each, if not possible, use for loop. Everything else is just super slow. Now, people often tell you that mutations are bad, and it's true. But there are cases when mutations are good. Just look at this simple snippet. So we have some fetch request that goes to backend. It fetches some large chunks of data. And this data actually represents users from GitHub. So each user has a nickname, and then the data for this user contains first name, last name, and array of repositories. Each repository is given by URL and by a flag whether it's private or not. Now what we want to do is, we notice that in our application we oftentimes are showing full name of the user, and we don't want to do these calculations over and over. Of course, there are different tricks for pretty much every framework how you can do this combined data fields, but let's say we want to change it initially so that we don't have to calculate it every time. Now let's say we want to take this collection and just inject the new field there. So how we can implement this? A normal way would be to just create a new object and then create immutable collections. So you would iterate over all the elements. You would take each user, you would spread it, you would inject the full name, and then don't forget that repos is an array, so you have to make immutable array out of that as well. Otherwise, this array would point to the original one, so you want to have like full, clean, immutable structure. The other way would be to maybe use JSON stringify with JSON parse to like really create a copy of the entire object and then inject this full name. Or you can simply mutate object, right? Because this is just the data that we got from the internet, we got from our backend. We haven't been using it anywhere, and it doesn't matter if it has been changed or not because we haven't started using it yet, right? So we can do all the mutations we want, and only then your application actually starts to use it. So it's safe to mutate it at this point. And if you would mutate this, the performance difference would be 6 times. So mutating this collection would be 6 times faster than using immutable approach. So wouldn't you agree that it would be useless to just go all the way with immutable collection where you don't have to? Now, often we hear this repetition is the mother of studying or learning. But as we know in development, repeating stuff is usually not a good thing. So again, we have our collection, and what we want to do is now we want to create a structure that shows us the connection between different users, who follows who. So we have an object where a username points to all the usernames in our collection, and if those two are connected, then we set the flag to true, otherwise we set it to false. Now, in order to do this, we can create the initial connection where we would just create like placeholders for each username, set it to false. Then we would create our network where for each username, we would spread the same connection, so our placeholder, and then we would have our special logic that actually tracks all the connections and creates our infrastructure. But one thing we might notice is that we are doing a lot of unnecessary data here, a lot of necessary calculations. Because setting field to false is the same as not setting it at all, because it's a false value. So we can assume that whether it's set to false or it doesn't exist at all, it comes down to the same. So instead of this, we can write something like this, right? For each username, just have empty object, which means that initially this user is not connected to anyone because there's nothing in the object. And the difference, merely 350 times. So remember, important thing is to skip all the necessary data and all the necessary calculations that you can, because no code is always faster than any code. You can take a picture of this code.
Wait.
Now let's talk about arrays and objects. These are our usual data structures in JavaScript. How do they compare? What do you think? Is the array faster or object faster? It's array. So this is a bit more complex structure that I used for a sequencer that I built in JavaScript during the COVID times, where the structure looks like this. So we have an array of instruments, and for each instrument I have a field that tells me what is the sound, so the path to the base file. I have a state, whether this track is on, off, or it's running solo. What is the volume, what is the pan, what is the pitch, and then 16-step sequencer, which tells me whether in certain period of time I should play this sample or not. Now I started initially with object, and then I realized there's a lot of jitter and my sound would often skip. So instead of getting pure 60 frames per second, I was barely getting like 10 or at best 30 frames per second. Which for graphics, maybe it's still acceptable, but for sound is not. Because what would happen is that instead of hearing the sound, you would not hear it because your compiler, your JavaScript code would just skip over the sequence. It would just say, oh, I need to catch up with this, and I'm gonna just skip this sound, it's fine. And then you like suddenly hear the rhythm that is missing parts of it, right? So this is how the data looks like, as I mentioned. So there's sound, state, volume, and I decided to replace it with an array. So this is the same structure exactly. It's just everything is written in an array. And there's no object, there's no field. So one might think, okay, this is probably faster, it's fine. But how do you read this stuff? Because it's just data. You can't say what each field represents. So you can specify your structure initially. If we do it like this, we can specify our array as typed array, where each field has a specific type in the array. And then we can also use constants that will tell us for each of those array elements what they represent. So previously we would call instrument.sound, for example, and now we're gonna call instrument of track sound, where track sound is just a constant that tells us that we want to look at the element on a position 0, but while you're typing in the JavaScript, you don't want to remember was it 0 or 1 or 2, you just want to use constants so that you don't mess it up. But objects are not necessarily bad. There are times when objects are shy, and this is the lookup tables. Imagine we have, again, this huge list, and what we want to do now is we want to create a function that for a given URL would tell us what is the nickname, what is the user that owns this. Now it would be simple if the URL already contained nickname, like here, but sometimes user creates a repo under some other name, some organization name, so we want to know also for these, where do they belong to. So we need to create some sort of way of going through the structure and figuring out where they belong to. And this is where we can create our lookup tables. So lookup table pretty much is an object that links to fields, right? So this is a simple associated array where we're going to say that for each repository URL, we're going to map it to the key to the user, right? So now when we need to find the user for the URL, we simply just call user lookup of URL. Right? So initially we have a bit more work because we have to traverse the entire structure to create this list. But then later on, whenever we need to grab the user, it's instant. We just look at the object. And this is very powerful, especially if you have to do something that keeps repeating over and over and over again. This is something that in my company we, for example, had for linter, where we have a bunch of projects in monorepo, and each of these projects has a bunch of files. And we want to know for each files, when you are imported, we want to know which project it belongs to. And this is something we keep doing over and over and over again. And it was super expensive, so we decided to just create a lookup table that would give this information instantly. So we create it once, and then as linter is running, or build is running, or any other process, just gives you immediately that project. And you can see whether they are in the same project or it's cross-project import. But what about the maps, right? You probably heard this new map. It turns out that you can do the same thing with map. Instead of using user lookup of square brackets, you use set and get to set the value and get value. And what is the difference? Table is 13,000 times faster than using normal search with the array, but map is 17 times faster than normal object. So whenever you can, use the map over plain object. On top of that, normal object can use only strings as a keys, strings, symbols, or numbers, while map can use any type of structure as a key. So you can, here, instead of URL, we could have put entire object or whatever. It's using referential equality, so you can put whatever you want in there, and that gives it additional power. One thing I didn't mention about array versus object. So when you're using array structure over object structure, like we use in the sequencer, that was 50% increase in performance. And finally, we come to higher order functions. Higher order functions in JavaScript are functions like, so let's look at the same structure again. So the higher order functions would be map, filter, reduce, so all of these functions that wrap additional functions from JavaScript. So in this case, they all wrap for loops inside. And this is very convenient, and I encourage you to use higher order functions for writing some code snippets where you don't care that much about performance because they are nice, they are clean, and it's super readable, right? So we take our list values, we first map each user values to repos, then we filter those that don't contain any repos, and then finally we spread all the repos and we take the URLs. So this would return us the list of all the possible URLs in our structure. It's very nice, it's very readable, but unfortunately, it's also very slow. Another approach would be to not use higher order functions, but use the plain array where we would collect things and then use simple for each loop. So we iterate over, again, all of the values, and then we iterate over all of the repositories if they exist, and if found, we just push it into this collection pod. And this gives us 200 times increase. Now, if we, instead of doing spread here, used immutable structure, so instead of spreading always this accumulator, but instead pushing stuff to the accumulator, so mutating this object in the reducer, it would be just 2 times slower. It would be still slower, but not 200 times slower, just 2 times slower. So this shows you how mutation matters in these type of things. So you might be wondering, how do I know all these things? Well, that's because I was doing a lot of performance detection, and usually it follows when there's a report that something is slow. Sometimes you just look at your code and think, can I make this faster? And then you look at your code and try to spot things that might be improved. Sometimes it's a hinge. Sometimes you know what you're looking for. The more you look at it, the better you become at it. But tools like JS Bench help a lot because you can create a small snippets where you can test your ideas. You can experiment. So what if I change this? What if I do it like this? Would it be faster or slower? And I keep using this constantly. So all of these QR codes that were in the slides, they all point to different benchmarks that I created. And finally, sometimes it's hard to do it in the benchmark because sometimes your tests include some data coming from backend or some very complicated situations that is hard to replicate somewhere like this in some sandbox. In this case, it's good to do time checking. So I use the console.time constantly. You can do also performance measurement, which is also convenient too, but it's more complicated. And this is as clean as console.log with new date, but a slightly more convenient, where you say console.time, you set some name, and console.timeEnd, the same name, it will print out the duration between those 2 points. So you can test some small snippets that you think are slow, or you can test the whole block of your function or even your entire module to try to spot what are the pain points. For example, if you have some complex functionality that you know it's slow, it's good to just spread these console times all over the place to find the exact lines in the code that are slow, because then you know where to focus. Otherwise, you'll be looking at a huge pile of JavaScript looking, whoa, something is slow here. So this is very helpful if you can't replicate it in Sandbox. If you can, use JS Benchmark because it runs in a bunch of iterations and it will actually show you the difference. The other thing is to use something like Hyperfine, where you can run the CLI command of your project, where you can specify how much you want cold time, how much you want warm time, and you just keep it running and it will tell you what is the average between different runs. There's a bit more information on my blog post that I released some months ago, which is called the butterfly effect, or how we gave the linter 100% boost. But it's actually a boost we gave after the first boost, which was additional 30 times. So it's like collective boost, which comes to some 3,000 times. So just to recap, know your loops, know to understand the loop, to know where the loop is and try to simplify them. Mutate whenever possible. Use arrays and maps smartly. Avoid higher order functions when performance matters, and skip unnecessary data. This was the slide.
Thank you.
Stay fast, my friends.